It was hard to stay close to family until Facebook Portal. Its smart camera keeps up with the kids on video calls, and it's designed for them to be heard loud and clear. But the best part is how close we all feel.
Give the gift of a deeper connection. Facebook Portal. Share something real.
Because study is better with play. Samsung Galaxy Tab S7 FE. Ready to make the most of your school year? The ultra-large screen gets you closer to the action, whether you're studying, streaming, or gaming. Seamless syncing lets you hand off calls, videos, files, and more to other Galaxy devices, like your phone. The included S Pen gives you a super smooth experience. Plus, choose a vivid color that shows off your personal style. Samsung Galaxy Tab S7 FE. Terms and conditions apply.
This episode is brought to you by Rad Power Bikes, designed to be a blast to ride and good for the environment. Rad Power Bikes have affordable e-bikes for every kind of rider. Get this year's must-have holiday gift at radpowerbikes.com.
Welcome to the New Books Network.
Welcome to New Books in Mathematics, a podcast channel on the New Books Network. I'm Corey Brunson, a host of the channel, and I'm talking today with Chris Blakely, author of Poems That Solve Puzzles, The History and Science of Algorithms, published in 2020 by Oxford University Press. This is a remarkably readable biographical and technical history of algorithms that I think must lie close to the Pareto frontier of accessibility and rigor, perhaps strategically or perhaps inevitably. Maybe Chris can tell us. The coverage builds naturally from the earliest algorithmic routines to the high-profile achievements of modern AI. I'm excited to talk with the author today through some of the selections from the book. Chris, welcome to the podcast.
Thanks very much for inviting me, Corey.
So to begin with, could you say a word about your own mathematical trajectory, and in particular, when you began to study algorithms?
Sure. So I guess I went through the usual mathematical education in school. It was really in secondary school and high school that I got interested in programming for the first time. My parents bought me a computer, a Sinclair ZX Spectrum for Christmas, and I taught myself how to program. So at that time, I didn't really appreciate what an algorithm was. I was just writing programs. But it got me the bug for computer science. So when I finished high school, I joined Queen's University Belfast in Northern Ireland to study computer science. And after that, I did a PhD degree in Dublin City University in the area of electronic engineering. And then I went into industry for about 7 years, working on chips and communications, software and hardware. And in 2003, I joined University College Dublin, where I still work. And I'm an associate professor of computer science. I'm currently head of the School of Computer Science at UCD. So I guess I've moved between academia and industry over the years. I enjoy research, but I also enjoy applying the algorithms and programs that I've developed to real-world problems.
And based on many of the stories from the book, that seems to be a pretty good background for the writing of this book. There's a fair amount of cross-cutting and cross collaboration between the academic sphere and the industry sphere. So let me ask, when writing this book, what were your goals and who was your target audience?
So the idea from the book came from a few years ago. I noticed in the news media, there were suddenly lots of references to the algorithms. And this struck me as strange because it was originally quite a technical term. So there were articles in newspapers about the Google algorithm and the Facebook algorithm and algorithmic bias and AI algorithms. And it seemed to me that a lot of people maybe writing the algorithms or writing the articles and even reading the articles didn't really understand what an algorithm was. They knew it was something to do with computers. They knew it was something to do with programs, but really didn't have any context. So I thought, a book would be really useful for people to inform them about what algorithms are and where they came from. So I set about writing the book, I suppose it's 4 years ago now. to try and explain to the general reader, so somebody with an interest in science and technology, but not a specialist, what algorithms are, and try to tell the story of how they came to be, and the history of the people and the projects and that led to the creation of these great algorithms that I find very interesting.
So let's begin getting into the content where you begin in the book. What is an algorithm?
So an algorithm is a well-defined sequence of steps that solve an information problem. So an information problem could be as simple as sorting a list of names into alphabetical order, or it could be as complex as trading cryptocurrencies. So there's a wide range of algorithms being developed over the years to solve lots of different information problems. But it's the idea that these problems can be solved by following these simple steps. And if you can solve a problem in that way, it's very powerful because you can write down steps. That means other people can solve the problem and can compare the way that you're solving the problem with how other people are solving it. And you can preserve that. If you write it down, it's preserved for as long as your document lasts. So it becomes a cornerstone for future developments and algorithms. And I think the importance of algorithms really transformed with the invention of the computer. So in the 1940s, first computers were built. And really what a computer is it's a machine that performs algorithms. So your algorithm, your sequence of steps gets encoded as very simple steps that the computer can perform one after another. And that will solve the information problem in the computer. Big advantage of the computer, of course, is it can perform these very simple steps at extremely high speeds. So you can get billions of these steps done in a second, where if you're doing it manually, you maybe get 2 or 3 done in a second. So algorithms went from being a mathematical curiosity to something that everybody relies on every day on their desktops and their smartphones. So algorithms are the basic concept of steps that's behind all of the software and apps that we use all the time.
And before getting into some of the earliest algorithms, which are focused on arithmetic tricks or arithmetic procedures, you do have a good tactile example in the introduction of book sorting algorithms as an illustration of not only what an algorithm does, but how they can be improved and honed upon and tested. So I wonder if you could talk through that case study. I know it's fairly common, I think, in introductions, but it's a pretty good place to start.
Sure. Yeah. So the example I use is sorting a pile of books into alphabetical order. Could be the alphabetical order of the author or whatever. So there have been a lot of different algorithms proposed over the years for doing that. Probably the one that most people use naturally without knowing anything about algorithms when they're given a pile of books to sort, to put on a shelf, is an algorithm where you just take a book at a time and you put it in the right place. So you pick up a book, you put it in the shelf, the first book, second book, you scan what's in the shelf to see where it should go, you insert it, and then you go on to the next book, you scan across the shelf, you see where it should go, you should insert it. So that algorithm's called insertion sort, not very imaginative. There's another algorithm that can do the same task called quicksort. And the quicksort algorithm performs the same task, but does it much faster. Doesn't make much difference for small numbers of books, but makes a significant speed up for large numbers of books. And the idea behind quicksort is that you go through your pile of books, sorting it into 2 piles. So you pick a pivot letter which splits the books into two piles. So anything that's before the pivot letter, let's say you start with the pivot letter of M, anything that's before the pivot letter gets put in the left pile. Anything that's after the pivot letter gets put in the right pile. So you end up with two piles, one with everything up to M and one with everything after M. So then you go to each of those piles and you perform the same operations. You split them into two piles. And so for the pile that goes A to M, your pivot is probably going to be J or something like that. And you split it into two piles. So you keep on doing this, splitting your piles into twos. And eventually you'll reach a point where every pile just has maybe 5 books in it. And you can sort them quickly with insertion sort. But the point is the piles are in sequence. So if you sort the first pile with insertion sort, the pile after it is the next few letters in the alphabet. The pile after it is in the next few letters after that. And while this algorithm quicksort is more complex to understand, when you actually apply it, it uses far fewer operations for a large pile of books. So in the example I give in the book, for maybe 1,000 books, you're reducing the time it takes for a librarian to sort from several days to an hour. It's that sort of transformative difference. So there are lots of sorting algorithms, but those are kind of two extremes. We have the simple to understand algorithm that's very, very slow, and we have this hard to understand clever algorithm that's very, very fast. Those examples allow me to illustrate what an algorithm is and the importance of clever algorithms to speed up tasks.
And we'll come to some very clever algorithms later on in the discussion. To begin with, now into the first chapter, ancient algorithms. What are some of the earliest, and I should stress, documented algorithms?
Yeah, and the documented is important because the oldest algorithms date from around 4,000 years ago. So this is a very long time ago. The reason that we know about these algorithms is they were originally written down on clay tablets. So etched, the algorithms were written in a language that we now call cuneiform. And the cuneiform, the symbols of that language are etched into wet clay. So they're wedge-shaped. The cuneiform term comes from, it's Latin for the term wedge-shaped. So they're wedge-shaped impressions on the clay tablet formed symbols. And those symbols are readable language. The algorithms were written in this way in clay tablets. The clay tablets were dried in the sun to preserve them and were lost thousands of years ago when the cities that they were written in fell into ruins. The clay tablets, the hard clay tablets, survived. They're like stone once they're dried out. So they survived in the ruins of these cities for thousands of years before being rediscovered by archaeologists. The language of the tablets had been lost in the interim. They were finally decoded and deciphered. And the tablets paint a rich tapestry of the life of the times. So we're talking about the region of Mesopotamia. So this is the land between the rivers and which straddles the border of modern Iran and Iraq. Over hundreds of years, the tablets document civic society, taxation, letters, contracts, all sorts of daily life. Amongst all of that daily life have been found some tablets that actually describe the algorithms that the mathematicians of the day invented. So those algorithms are the oldest known account we have of using step-by-step procedures to solve information problems.
And what were some of the information problems that these earliest algorithms were written to solve?
They solved practical problems, so construction problems, and also astronomical problems as well, and tracking the stars and sun. And also even things like taxation and interest calculations were documented in this way. The example I give in the book is calculation of the sides of a rectangular cistern, presumably of water. And the way it was written is very similar to the sort of problems you see in a mathematical textbook today. There's a statement of the problem, what you have to do. There's a statement of every step that you have to take. And then at the end, there's this statement, that is the procedure. And it's kind of like a sign-off. Nowadays, sometimes mathematicians use the Latin QED to sign off. It's like a sign-off at the end. So the example that I have, the cistern calculation, you're given some information and some information is missing. And the procedure calculates the missing information. The nice thing about it has an embedded example in there, a numeric example that helps you follow the procedure. And people think that these clay tablets were written by students working with scholars, learning how to do their mathematics. So, it could well be that this was essentially a student's notebook from 4,000 years ago.
And I couldn't help but notice reading some of these algorithms that as they presage modern textbooks, they also seem to already have most of the basic components we think about algorithms having. The use of iteration, the use of recursion, the use of storage or memory to keep track of terms that will come back to be used later. Is that fair to say? Are there really basic components that have only come about in the past few hundred years?
It is true to say all of the basic operations are there, with the exception of if-then-else decision-making operations. So those aren't explicitly called out in the tablets as far as we can see. Now, the Babylonians did document if-then-else statements in their omens, so that their omens are like the superstitions. If a man stands on the hill, it's a good omen. This sort of thing. So they do possess the if-then structure, but that's used for omens and laws and things like that. It's we don't see it to date being used in algorithms. So they had the concept, but it wasn't applied. So when you're missing the decision-making element, it's like you're more geared towards procedural calculations in terms of what you can do with the algorithm.
Jumping ahead to chapter 3, and I'm going to take a couple of stories from this chapter that I thought were really interesting. You recount how Charles Babbage and Ada Lovelace, names who will be familiar to anybody who studied algorithms, and later Alan Turing came to postulate and to write programs for what they may or may not have called, in these words, general purpose computing machines. So I hope you could give an abbreviated account of how they separately arrived at their projects.
Sure. So Babbage proposed what he called the analytic engine in 1837. So 1837, you're talking about more than 100 years ago, before the first real computers. And what he proposed was a steam-powered mechanical computer. So he'd taken two ideas that were around at the time. One was the idea of the mechanical calculator. So desk calculators had been invented previously and were manually operated to do simple calculations. But they were, individual calculations. It was a sum was done or a multiplication was done. And the steam engine had been invented not long before Babbage's work in this. So we were talking about in the context of the Industrial Revolution. So Babbage put these two ideas together. Well, if we took a mechanical desk calculator and we powered it with a steam engine, why couldn't we get it to do a sequence of operations one after another and reuse the results, the intermediate results. So you can see there the idea of a computer, and he applied the idea of punched cards to store the data and the instructions. And that idea came from Jacquard's loom, which was invented as a programmable loom that could vary the way that the texture was woven. So Babbage took those ideas, proposed this machine, and tried to get it built. He'd worked on a previous machine called the difference engine, and it had been funded by the British government. The difference engine was it wasn't a true computer; it was really a calculator. The analytic engine was more advanced and really was, had it been built, was really a computer. It could support all the operations that a computer needed, including the decision-making function. Now, what happened with the difference engine was there were Babbage's and his assistant were unable to complete building it because of the difficulties of manufacturing mechanical pieces with that sort of accuracy. So building a mechanical computer requires very high precision, cogs and gears, etc., and levers, and it just wasn't practical using the technology of the day to fabricate those pieces with that sort of precision and reliability. So the difference engine construction failed. The analytic engine construction was never funded. So although Babbage had the idea and worked on it for many years, it never came to fruition.
And actually, if I could interject with one question, one of my favorite parts of reading this chapter was learning how, in the absence of a working or even prototype device, these researchers were able to test whether their programs actually performed the operations they were intended to.
That's right. So Charles Babbage and Ada Lovelace actually wrote programs for this imaginary machine, this machine they'd invented but didn't exist. So they knew what instructions that it would support, and they took some algorithms that they're familiar with, mathematical calculations, and actually wrote the programs to do the computations. And so we one of the primary sources of Babbage's ideas on the analytic engine comes from a paper that Lovelace wrote describing the machine. And in describing the machine, she included the programs in an appendix and actually instruction traces. So by hand, they were doing calculations, applying the calculation. Once this instruction is performed, we get these results. Once this instruction is performed, we get these results. So it allowed them to prove that the machine would be capable of doing the computation had it been built. And that idea of tracing programs, we still teach it in first year in computer science here in UCD and everywhere else. So that's held as the way to do these things. So if we move forward to Turing then, so we're moving forward 100 years to when Turing proposed what's now called the Turing machine in 1936. So almost 100 years between the two proposals. So what Turing did, he didn't try to build a machine. So this was well before the outbreak of World War II. What he did is he wrote a paper that described an imaginary machine. And he didn't try to design a practical machine in this paper. It was a intellectual construct, an imaginary machine. And what it was a device that could be operated by a human that could perform algorithms. So you could give the human a series of instructions as to what to do with the machine. And if they carried it out, that would apply the algorithm. So the machine was used by Turing to reason about what such devices could and couldn't do. So the Church-Turing thesis states that any real-world computation could be translated into an equivalent computation involving the Turing machine. So this is really interesting. What they said is the Turing machine can do any algorithm, and then the reverse of that is true. If the Turing machine can do any algorithm, then an algorithm is anything that a Turing machine can do. So this became the modern definition of a computer. It's a real general purpose computer if it can perform the same tasks as a Turing machine. And if it can perform the same tasks as a Turing machine, then it can perform any algorithm. So the paper used this idea to make some proofs about what you can and can't do with computers, and they're fundamental truths that we still rely on in computer science. So that machine was never intended to be built. Turing was involved in designing computers during World War II. He was involved in designing the bomb, which was used to decode the German Enigma machine messages. The bomb itself was not a true computer. It was a calculator, an automatic calculator. Turing, after World War II, he left Bletchley Park, where he was working on cracking the codes. And he joined the National Physical Laboratory, and he led a team that was trying to build a computer, a real computer. They failed in part due to the difficulties of working with Turing, and Turing moved back to ultimately to Manchester University, where he joined Max Newman, who had worked with Bletchley, with Turing at Bletchley, and also worked with him, being his supervisor as an undergraduate student. Manchester University had constructed their own computer, and when Turing joined them, he was actually more involved in programming the computer than constructing it. Turing was involved in another computer being designed at Bletchley Park called the Colossus machine, but he wasn't the main designer there. So what you can say is there's a beautiful symmetry there. So Turing actually failed in building a computer as well as Babbage. So Turing's key attempt to lead the construction of a computer was at the National Physical Laboratory in London, and that project actually failed. It was actually when he worked on the software at Manchester. The bomb wasn't a real computer, and he didn't really work on the Colossus. So you have this symmetry, these great ideas not coming to practical fruition 100 years apart.
The symmetry really came out of the chapter, and something it prompted me to want to ask you is to take the researcher's points of view, in addition to the way that their work played out in practice. So if you could put Babbage and Lovelace in one hand and Turing on the other into conversation, would they say that they were engaged in the same enterprise? Did they have the same goals and the same long-term vision for what they were doing? Yes.
So Turing was aware of Babbage's work. He actually mentions it in one of his papers. And it's clear, like, he very much admired Babbage's and Lovelace's work on the computer. And, you know, in the paper, he it's clear he thinks what he's doing mirrors it in some sense. And he acknowledges, this was 100 years ago. So Turing very much saw it that way and admired Babbage and Lovelace. What would Babbage and Lovelace have thought about Turing? I think Babbage would have been very interested in what Turing's was doing, and Babbage was also, he was quite a socialite. So he talked to all sorts of people at all sorts of stations in life. So I think he would have got on very well with Turing. Whether they could have worked together, not so sure. Babbage changed topic an awful lot during his life. He never really stuck with anything. He did lots of different things. And Turing, he has a reputation there. So I don't think they would have worked together, but I think that they would have been very interested in each other's work.
That's interesting to think about. Thank you. So, in addition to some very well-known stories, the book includes many, I was impressed by how many lesser-known stories in the development of algorithms, and I wanted to get into one of them next. When we think about the history of mathematics and weather forecasts, at least I, most often think of Edward Lorenz and the origins of chaos theory. But Lorenz's observations were surprising in the first instance because there was a quite mature branch of mathematics that had been developed to forecast weather by that time, with its own embedded assumptions. So, could you tell this story, beginning from Lewis Fry Richardson and on to the early computer forecasts?
Yeah, sure. So you're right. I think Lorentz is well known for being one of the originators of the science of chaos. So this idea of the butterfly effect, where you have a system that's highly dependent on initial conditions. A small variation in initial conditions causes a large change a few days later. And this is linked with weather forecasting. So Lorentz discovered chaos accidentally on a computer simulation. And what he was doing is running simulations of how the weather would evolve over a period of time. He ran the simulation once and got results from that. He ran it again and he got completely different results. And at the time, computers weren't terribly reliable, so he thought something was wrong with the computer. Couldn't find anything wrong. And eventually he discovered that the difference was that he had applied a different rounding to the input numbers of the initial conditions. So he started to look into this. This was a real effect. And it led him to the conclusion that in the weather, small changes in current conditions lead to big changes in what the weather will be a few days later. And this is the fundamental difficulty in accurately predicting the weather, even over the course of a week. Now, what he was doing there, he was running numerical simulations of the weather forecast. So, in numerical simulations of the weather forecast, what you do is you take the atmosphere, you divide it up into cells, and for each cell, you say what the average pressure, temperature, wind velocity, etc., is within that cell. So then you have these measurements for this 3D grid of cells, and what you do in your calculation is you move forward in a series of time steps, and at each time step you calculate what the current conditions in each cell are going to be, and that calculation for a cell is dependent on what's happening in the cells around it and how much sunshine it's getting and things like that and what its neighbors are doing. So that calculation evolves over a period of time. That idea wasn't Lorenz's. The idea of using numerical simulations goes back to Lewis Fry Richardson, who was born in 1881 in Newcastle in England. And after graduation, he worked on short-term research positions for a while, but in 1913 he was appointed superintendent of a weather station in southern Scotland, Eskdalemuir. It's the middle of nowhere, very windswept and stark location. And Richardson's duties were to monitor the weather, seismic vibrations, and the Earth's magnetic field. So he had a house and lots of spare time, and he started to think about the problem of forecasting the weather. So he was the first one to really develop and apply the idea of a numerical algorithm for forecasting the weather. So the first person to really take on this challenge of dividing the atmosphere into a grid and calculating what those volumes of gases were going to do based on the laws of physics. He took some data that he had for the weather over Germany in 1910, and he ran this simulation doing manual calculations. And this took months. I mean, we were talking about a large area, and he was trying to figure out what every cell was doing by doing calculations. At the end of all this months of work, his calculations were terribly inaccurate. There were surface pressures that just weren't feasible. and it didn't match how the real weather had unfolded over Germany in 1910. So he pressed ahead and wrote a book about this experiment that he'd done in 1922. And in it, he actually envisaged a great hall with 64,000 human computers, all using mechanical calculators to compute the weather forecast in real time for the entire globe. So ridiculous. I mean, 64,000 computers, and his results were inaccurate. So the book was just not well received. People thought this was all a little bit outlandish. That sat almost unnoticed for 30 years until John von Neumann picked up the idea for one of the applications for his new computer at the the Institute of Advanced Studies in Princeton. The Princeton computer wasn't ready quickly enough, so he and a team performed numerical calculations of the weather on ENIAC, which was one of the first computers. And those calculations were done in 1950 and proved to be not completely accurate, but reasonably accurate numerical simulations of the weather as it unfolded in North America over 4 days in 1949. So, in a nice touch, one of the key people in that team, Charney, sent a copy of the paper describing this ENIAC forecasting to Richardson, and Richardson wrote back to say, to congratulate the team and admiring their enormous scientific advance on his own single and quite wrong result. So that's 1950. So that's well before Lorentz. So Lorentz was using the same sort of simulation as von Neumann's team had used in 1950, and that was all based on the ideas that were first experimented on by Richardson in the 1920s.
Now, there's a lot of interesting stories, very interesting human stories as well, in the early emergence of machine learning and artificial intelligence. And some readers might be surprised to learn just how far back that emergence traces. I wanted to specifically ask about an implicit distinction that you make in this chapter. This is chapter 5, between machine reasoning and machine learning. What it tells me is that even as these very first thinking machines were being designed, what it means to think was already a subject of contestation. Is that right to say? And could you describe how these early machines thought?
Yeah, that's true to say. I mean, this debate about computers and the human mind and the human brain was there from the very start of the invention of the computer. So ENIAC, which, as I say, was one of the first computers, it was invented or built in the University of Pennsylvania in the US during World War II and was unveiled to the press in 1946. So the headlines in the press the next day were about the Army's new wonder brain and its inventors, and electronic brain computes 100-year-old problem in 2 hours. So the press were very much thinking of this as a computer as a new brain, an artificial brain. The researchers were also thinking about the implication for sure. So in 1950, Turing published a paper called Computing Machine and Intelligence, published in a journal called Mind, which grapples with the questions around machines and the mind and what the difference is and how do you tell them apart when you have a really powerful computer. So, for example, in that paper, I have a quote here, the original question, can machines think, I believe to be too meaningless to deserve discussion. Nevertheless, I believe that at the end of the century, the use of the words and general educated opinion will have altered so much that one will be able to speak of machines thinking without expecting to be contradicted. So Turing was predicting the whole speed up and evolution and improvement of what a computer could do, and the whole of AI and that computers would be, in everybody's view, thinking by the year 2000. So he was a little bit ahead in his predictions, but I think given the scale of what he was talking about, it was very impressive. So he was considering this idea of, do computers think, back in 1950. And what he was saying is, to him, thinking was irrelevant because people would just believe that the machine was thinking or treat it as if it was thinking. Von Neumann, who, as I mentioned, worked on the ENIAC and developed his own computer in the IAS, wrote a book on the topic as well. It was published after his death in 1958, and that book was called The Computer in the Brain, and it compared the operation of digital computers and neurons in the brain. So really drawing together very current, at the time, work, and still relevant today. Unfortunately, it was unfinished. It'd be very interesting to see how he intended to bring those ideas together. So that was a loss. But he was thinking about this sort of thing in the 50s, as to what the distinctions between the brain and computing.
The passage from Turing is especially interesting. At the present day, the usual comment about AI, in my experience, is that intelligence tends to be defined as what a human can do that a computer yet can't. And Turing seemed to have the opposite expectation of how we would think about these devices in several decades afterwards.
Yeah, so I think for me, the key question in all of this is whether what's going on in the brain is a computation or not. So if it's computation, then it could be replicated by a Turing machine once we know what the algorithm is. So is the brain running an algorithm? If it is running an algorithm, then we can replicate it on something that's equivalent to a Turing machine, which is a computer. I mean, there's questions about trying to build a computer with the brain's processing power. We're not quite there yet, but we're getting very close. But what we're missing here is the algorithm. We don't really know how this works. I mean, we've made great advances recently with artificial neural networks, which are modeled on what the brain does. But, it's a very simplified version of what the brain does. And it's not at all. I think the researchers in the field don't think that the brain is just a massive artificial neural network. We're not just going to get there just by throwing more and more processing power at this. We've got to actually rethink the algorithms and improve the algorithms, and that's the path to improved artificial intelligence. So there's this fundamental question: is everything that's going on in the brain computation or not? We know that some of it is, because we can replicate it with computation. There are researchers that say that things like consciousness are not a computation and can't be replicated. There are researchers that say that consciousness can be replicated. It's just an illusion, and it can be replicated with computation. So that there's no answer to that yet. That's still a philosophical debate. But certainly some of the things that go on in the brain can be replicated with computation.
The ability to put enormous computational power into these algorithms, in part, I think, is responsible, or I infer is responsible for the importance of understanding and classifying how the speeds and the requirements that these algorithms come with. So while the headliner of the next chapter is, and I'm sorry, I've never pronounced his name, Dijkstra, thank you. Dijkstra's root finding algorithm. I think I gained the most from your very lucid explanation of complexity classes that Dijkstra's was used in part to motivate. So could you tease apart these classes?
Sure. So In the example of the sorting books into alphabetical order, I compared two algorithms, insertion sort and quick sort, and I said that they perform the same task. It's just that one of them does it with less operations than the other. So when we talk about algorithms, we often compare their what we call computational complexity. So the computational complexity of an algorithm is the number of operations it takes to complete. And the number of operations that an algorithm takes to complete depends on the size of the problem. So in the case of the book sorting algorithm, the size of the problem is the number of books. Okay, so if you plot a graph with the size of the problem along the x-axis and the computational complexity along the y-axis, as the size of the problem increases, inevitably the number of operations required to complete the task increases. Okay, so there's a dependency there between size of the problem and computational complexity. Now, how quickly that curve grows is really, really important for the algorithms. So if you have an algorithm where the computational complexity grows very slowly with the size of the problem, that means that you can complete the algorithm in a reasonable amount of time, even for large sets of data. So in the book example, quicksort is what we would consider a fast algorithm, and you can use quicksort to sort a large number of books in a short time. There are other problems outside of the problem of sorting books where the best algorithm that we've found is still quite slow. It still has a high computational complexity. That means that the rate at which the computational complexity grows with problem size increases very quickly. And for those problems, we can solve them for small numbers of inputs, but because the computational complexity grows so quickly, we can't possibly solve them for even moderate numbers of inputs. So the Dijkstra's algorithm that you touch on is an algorithm that's used to determine the shortest route between 2 points on a map. So it's used in navigation apps on smartphones nowadays, a variant of it. And what you do with the algorithm is you give it a map. So in an example I use in the book is a map of Holland with the cities marked on. You know the distances between all the cities. You know you want to get from, let's say, Amsterdam to Eindhoven. What's the best route? So the algorithm scans through the map and determines what the shortest route is between Amsterdam and Eindhoven, what cities, intermediate cities you need to go through to get there in the shortest distance. The algorithm for doing that, it checks at each step. It assesses the routes to the neighbors. So the algorithm starts at the beginning point and assesses the distance to each neighbor. It then moves on to the neighbors in turn and assesses the distance to each of its neighbors and progresses in that way. And at each step, it writes down the route taken so far and the distance. And the trick in the algorithm is that it only updates the route and the distance if the newly calculated one is better than the one that's already written down beside the city. So it very quickly determines what the fastest route is by eliminating bad routes as soon as possible or slow routes as soon as possible. And that algorithm is much quicker than an alternative algorithm, which is the brute force search. You list all possible routes and you calculate which one is the shortest of all possibles. So you have these comparisons that you can do between algorithms, and you can actually measure their computational complexity. So what you're doing there is seeing how computational complexity varies with problem size. So if we imagine that graph with the x-axis and the y-axis, some algorithms that the computational complexity grows reasonably slowly are called polynomial time algorithms. And that means polynomial time algorithms are reasonably tractable. We can do pretty big problems with the algorithms that we know today. There's another class of computational complexity, which is called where the rate at which the computational complexity grows is much faster. And these are problems in which the rate of growth is perhaps factorial. Okay, so the rate of growth is very, very quick with problem size. So if we go back to Dijkstra's algorithm, the brute force approach there is a factorial increase in computational complexity. So what we can do is we can classify algorithms according to what's the fastest, we can classify problems according to what's the fastest algorithm for solving them. Okay, so if an algorithm can be solved in polynomial time, it's called, it's put in the P class. It's called, if an algorithm can't be solved in polynomial time, if a problem can't be solved in polynomial time, it's called an NP problem. There are some others there. I won't go into the details of them, but those are the kind of two primary classes. So P-class algorithm problems can be solved reasonably quickly for reasonably large data sets. NP algorithms are very slow to solve, even for moderate numbers of inputs. And what researchers have been working on is to try and find ways in which they can solve NP problems in P time. So that's finding a faster algorithm to perform the same task. And it's proven, there's been a lot of theoretical work in this, but it's proven very difficult to find P solutions to NP problems. And there's actually a $1 million prize available from the Clay Mathematics Institute of Cambridge, Massachusetts. It was initiated at the millennium. And if you can prove that a way for an NP problem to get solved in P time, you'll win the $1 million prize. Or else, alternatively, if you can prove that an NP problem cannot possibly ever, the hardest of the NP problems can never possibly be solved in P time, then you also win the prize. So if you can prove or disprove this P versus NP problem, you'll get $1 million.
And I'll say, for readers interested in the other subtypes of computational complexity, do read the book, because they are just as clearly explained. So Dijkstra's algorithm also leads conceptually into the next chapter, in which you discuss efficient communication across computer networks. And I think the interesting question that was answered in this chapter for me was, why isn't a shortest path algorithm sufficient in this setting?
So shortest path algorithms are now used for routing data across computer networks. There are actually variants in Dijkstra's algorithm, so there are slightly better ways to do route finding than Dijkstra's algorithms, but they're variants, they're extensions of his algorithm. The reason why shortest path algorithms needed to be adapted for routing in computer networks is due to the requirements of the problem. So in computer networks, the decisions as to how to route packets are being made at network points that are dispersed geographically. So you need to make a decision at the local switch. You need to make another decision at the campus switch. Then you need to make a decision at maybe a national switch as to where to send a packet. So those devices are all making their own decisions about where to send packets, and together they ensure that the network operates properly. So this is what we call a distributed system. So instead of one computer making all of the decisions on its own, we have lots of computers that interact to collectively make the right decision. So distributed systems are, by their nature, quite complex. So the decision being made by the algorithm, the routing algorithm, have to be distributed across all these nodes. You have to ensure that there's only small bandwidth used in exchanging probe information between these nodes. If you kept sending lots of data to measure the behavior of the network, you could probably figure out the routing a little bit better, but you would have a cost in terms of the overhead of sending all these probes out to figure out how the network's behaving. So you don't want to send too many probes because that uses up bandwidth. And then also most of these routing devices have to be pretty cheap, so the algorithms have to be low complexity, and they also only have low storage on them. So you don't want to have to store the shortest route to too many network nodes, because that's very expensive. So Dijkstra's algorithm was originally designed for the scenario where it was running on one machine. The one machine has complete information. In the routing case, you're designing for lots of machines and they've incomplete information, and you want either very constrained devices computationally. So it's these kind of variations and requirements that lead you to slightly different solutions.
So in a later chapter, you touch upon an event that many listeners will recognize, and that is the competition of IBM's Watson with several human participants at Jeopardy! So could you explain what the major problem its designers faced was and how they solved it?
So the major problem is dealing with the variability in natural languages. So there are so many ways to express a concept or a question with the same meaning, but just using different words. So what they were doing was trying to relate an answer to a question. So this is the idea of the Jeopardy! Quiz show. For anybody that doesn't know it, is the presenter gives an answer, and the contestants have to figure out what the question was that produced the answer. So it's kind of backwards to a normal quiz show. So what the researchers were trying to do with the Watson computer was develop software that would figure out what the question was. So the approach they took was to store a huge database of information. So they downloaded textbooks, encyclopedias, religious texts, plays, novels, movie scripts, all sorts of information to the computer. So this was a large IBM computer. IBM sponsored the work. It was their research team that did it to prove the capabilities of their most modern machines. So they had a large up-to-date multi-node computer at their disposal. They downloaded all this information, stored it in the computer, and then they had to write software which would somehow take this answer and relate it back to the question. So the team spent years at this, and the solution is really a collection of a lot of different approaches. So they have a technique in there called expert systems. They have another technique in there called case-based reasoning. And they even have some artificial neural networks in there as well. And what they do is apply all of these different techniques, score the results, and then the result with the highest score is the one that they rephrase as a question and output as the result to be given back to the presenter. So just to distinguish between the different approaches, so expert systems are rule-based systems used in the 70s, particularly for artificial intelligence. And they're based around writing programs that have lots of if-then-else statements in it. So if the input is this, then the answer is this. So it's quite conceptually quite easy, but the problem is those systems are very, very brittle. If the input matches an if statement, then they give a great answer. But if it's slightly different, then they give a terrible answer. So they're very, very brittle in the answers they give. Then the other type of approach, the case-based reasoning approach, is like a matching algorithm. So what the software tries to do is match the keywords in the answer provided by the presenter with the text held in the information base. So whenever the algorithm scores, so basically if keywords match up between the answer provided and an article from Wikipedia, let's say, then that gets a high score. So the keywords match. So what it's discovered is there's some sort of relationship between these two, and maybe the information in that article can be used to generate the question. The advantage of case-based reasoning is the if you like, the engine that does the analysis is always the same. It's really this matching and scanning algorithm, and you can give a case-based reasoning system a whole other context by feeding in a different encyclopedia. The matching is the same. You're just scoring and matching keywords between the prompt provided and what's in the information base. So I suppose looking back at it now, that IBM Watson demo was really a moment in time when these older systems, expert systems and case-based reasoning systems, were dominating. And very soon after that Watson Jeopardy appearance, suddenly there was a massive uplift in artificial networks. And I mentioned that there were some tiny little artificial networks in Watson, but they weren't used to any great extent. What really changed artificial intelligence was after Watson, the move to much larger artificial neural networks. And I think if somebody was trying to do Watson now, they would be predominantly artificial networks and a little bit of expert systems and maybe a tiny, tiny bit of case-based reasoning as opposed to the other way around.
And that leads really well into a question about your last substantive chapter. There are several chapters and subchapters that deal with competitions between computers and human players in different games. And as you describe it, AlphaGo's tournaments mark the pinnacle of this kind of competitive computer gameplay. The move from AlphaGo's original incarnation to AlphaGo Zero marked both a simplification and an improvement. So I wonder if you could describe AlphaGo's neural network infrastructure. It is a neural network-based, an ANN-based system, and how it was surpassed by something with less complexity.
Yeah, so AlphaGo hit the headlines because it beat a top 3 human player at Go. So it had been considered that Go was the most complicated board game, and that computers couldn't challenge humans for another 10 or 20 years. All of a sudden, DeepMind, a London-based company, came along and shattered that illusion. Their program, AlphaGo, defeated Lee Sedol over a 5-match competition. So that caught the headlines. And of course, then the news media moved on. a little bit later, about a year later, the team from DeepMind published a paper describing AlphaGo Zero. So AlphaGo Zero was an update on AlphaGo. The hardware was pretty similar. What it changed is the algorithms. And looking at the description of AlphaGo Zero and the original AlphaGo, I think what we can see is the team learned so much about how to do this problem, and they were really pressed for time to get the competition working. And when they finally took a breather after the competition, they went, "Oh, we could do this so much better. There's so much fixes we could put in." So they took a year to put in all these fixes, and they came up with AlphaGo Zero. And you're right, AlphaGo Zero is in a lot of ways simplifies things and gets rid of a lot of complexity that they didn't really need. So AlphaGo used two very large neural networks. AlphaGo Zero used one neural network with what we call two heads. Where the original had a policy and a value network, AlphaGo Zero uses one network for both policy and value, and it just outputs two values. So it's just the last few layers are different in those two networks. So it's sharing information. So if you're sharing information between two networks, it's faster to train. And they also...
When you say policy and value, you're talking about what decision to make and what predictive values to the outcomes of those decisions are fed into that decision?
So a policy network guides the system in what next moves are worth considering. And a value network assesses what the best move is. So there's a relationship there. The purpose is a little bit different. In a policy decision, you want to avoid missing any moves that might be really good down the line. In a value network, you can't look ahead any further. You just need to make a decision. So this is right. I think this is the best. I'm not gonna explore anything. I'm not gonna recommend anything that's a maybe. Just this is what I think. So similar, evaluating the position on the board, but with slightly different goals in mind. So that was one change. Another change was they threw out all of the human-based training. So in the original version, they used a database of human-played games that was available on the internet. So they completely ditched that. So it didn't learn anything from humans. It only learned from playing other versions of itself. So self-play using what's called reinforcement learning. So it started totally randomly and just taught itself to play by playing hundreds of thousands of games against itself. And the other thing they ditched was the rollout lookups. So these are a collection of positions where they had stored a table of how good they were, the probability of winning based on previous knowledge. So what they're doing there is again throwing